Hi everybody, let's look at this one from 2008. So we got a block of mass 2 kilograms and a block of mass 8 kilograms that are connected as shown above by a spring of spring constant 80 newtons per meter. So all of that seems like that is some important information. The spring is negligible mass, the system being pulled to the right across a horizontal frictionless surface by a horizontal force of 4 newtons there, with both blocks experiencing equal constant acceleration there. Okay, so let's start to solve these here. First up here, it says calculate the force that the spring exerts on the 2 kilogram block. So let me pull this picture actually back that I just threw away here. This whole system is going to accelerate the same, it says. This 4 newtons moves the whole system of 10 kilograms. The spring is only responsible for those 2 kilograms right there. So let's set up a Newton's second law situation here. So the acceleration of the system is equal to the acceleration of the second block, I'll call it there. So now, as we substitute in Newton's second law here, this is to say that the sum of the forces on the system divided by the masses of the system must be equal to the sum of the forces on the second block divided by the masses of the second block there. So if we get rid of friction and normal force cancels out with gravity down, then the only force on the system was that 4 newtons pulling it forward there. The mass of the system is both the 8 and 2 kilogram blocks together, so it's 10 kilograms. And then over here, the only force on the second block is the force of the spring. And the second block's mass is actually 2 kilograms. And so I simply multiply my 2 up to the other side. So 4/10 is the same thing as 2/5. Multiply that by 2, you get 4/5, or the force of the spring is 0.8 newtons. You could also think about this in terms of proportional reasoning. So since 4 newtons accelerates 10 kilograms, then to move only 2/10 of that, or 1/5 of the mass, we only need 1/5 of this force right there. And so that would also get you back to 0.8 newtons there. Okay, so next part, it says calculate the extension of the spring. We need Hooke's law for this. We just found the force of the spring, and we know that that is equal to the spring constant times the displacement. And so now we can just rearrange this to solve for x. So it will be the force of the spring divided by the spring constant. That force of the spring we just solved for was 0.8 newtons. The spring constant they told us was 80 newtons per meter. And that will give us finally that the distance it stretches is 0.01 meters there. All right. So part C here, it says the system is now being pulled to the left as shown below. So we're pulling on the 2 kilogram block instead of the 8 kilogram block. It says both blocks again experiencing equal acceleration. So is the magnitude of the acceleration greater than, less than, the same as before? Well, it is going to be the same as before. And let's think about our argument in physics court. Justify your answer. Well, we have the same force on the system, 4 newtons. We have the same mass of the system, 10 kilograms. So we're going to have the same acceleration according to Newton's second law here. All right, so the whole system will still accelerate the exact same value as before, which we never even actually found that so far. But anyway, all right, now it says, is the amount that the spring stretched greater than, less than, or the same as before? So this one is going to be greater. And let's use our physics court argument again. We have, as we just said, the same acceleration of the system, which means we're also going to have the same acceleration of block 2 as before, but now we've got more mass in block 2, which means we're going to need more force of 2 to move that, or this is also the force of the spring. Same thing there. So Newton's second law again here, sum of the forces over the mass. Since we just said that this didn't change, but the mass went up, the force will also have to go up to keep that 8 kilograms accelerating with the system there. And therefore, actually, so let me say one more thing. I shouldn't leave this off here. Since we need more force, then the actual question here, I got to keep going. I almost went off without finishing it here. More force is more stretch length here, according to Hooke's law. All right. Now we're ready to go on to the next one here. So this one, probably when we cover this problem, we won't have covered energy and you won't be able to answer this one. But just in case, we get this one later in the year. This is a conservation of energy problem. We had some amount of initial energy and that cannot be changed here. It's going to go into another form of energy. The original form of energy was kinetic energy, and that's going to go into elastic potential energy here. And so now we can plug in for each of our equations. Kinetic energy is 1/2 mv squared, and elastic potential energy is 1/2 spring constant times x squared. We can get rid of these halves here and move our equation around to solve for x. That is going to be the distance that the springs compress. So what was kinetic energy is going to get stored in spring energy of the compressed spring. So let's see here. We get mv squared. I'm going to divide my k down to the other side. I've got x squared here, so I have to take a square root. And now we are ready to start to plug in. One thing to keep in mind as we start to plug in here is that you can imagine that as this whole system moves off, some wall or something will stop to 2 kilograms, so we don't consider that mass there. The spring is going to be responsible for stopping the 8 kilograms there. And so the mass that we plug in here is 8 kilograms. The speed, as they said it was going, was 0.5 meters per second, and that gets squared. All of that goes over the spring constant, which was 80 newtons per meter, and that winds up giving us a distance of roughly 0.16 meters, depending upon where exactly you round it off there.